I hope you're all having a great morning today. I am Mr. Ish. Thank you for joining me. We're continuing here with the two questions here. Homogeneous differential equations, the purpose being to solve them for additional practice. You have 2x dy over dx is equal to x plus 3y. This item here shows it to be first order differential equation and you have to solve it. When you're solving it, you're taking the dy over dx on this side, you're holding it, but you're taking everything else on the other side. You have x plus 3y divided by 2x. You cannot clearly separate these variables across that equal sign, therefore you will do this substitution where y is equal to vx, and you send this through its derivation or derivative, you get dy over dx. By means of the product rule for this, you'll get v plus x dv over dx. But the initial item to keep in mind is this, y equals vx. You would substitute that right here. You'll have dy over dx is equal to x plus 3vx, because I've substituted y for vx over 2x. In this numerator, you can isolate an x. You'll have 1 plus 3v over 2x. You see how these x's will cancel out? You'll have dy over dx is equal to 1 plus 3v over 2. This is equal to that, and that right there is equal to dy over dx. Therefore, both of those items are equal to each other. You have v plus x dv over dx. Take this v onto the other side and do a common denominator. 1 plus 3v over 2 minus v over 1 is equal to x dv over dx. When you do the common denominator, it's 2. You'll have 1 plus 3v minus 2v is equal to x dv over dx. You can simplify the numerator item. You'll have v plus 1 over 2 is equal to x dv over dx. Now you can clearly separate the variables across the equal sign. You'll take the x on this side, you'll take all of this on the other side. When you do that, you'll get 1 over x, and here you'll get 2 over v plus 1 dv over dx. That right there represents the variables which have been separated, which can now undergo the simple integration procedure. And let's do that. I'll just create some space right over here and we'll then integrate this. You can integrate this, and let's do it. You'll integrate this, you'll have a dx, you'll integrate this, you'll have a dx here. These will cancel out. You just integrate that. When you're integrating the 1 over x in terms of its antiderivative, you're getting natural log x plus c. When you're doing this, 2 over v plus 1, it's not hard. You can just do 2 natural log v plus 1, right? That's exactly what you have. But what is v? If y is equal to vx, v is equal to y over x. And you can bring that right over here. And I'm going to bring it right over here. You'll have y over x plus 1. You can do a good substitution here for c. If c were equal to natural log a, you can do natural log x plus natural log a is equal to 2 natural log y over x plus 1. You can do all of that. You can combine these under a common log by means of their product. Also notice very well this fact right here. This 2 can come right here as an exponent using the properties of logs. You basically have natural log ax is equal to natural log. You can do a common denominator here. 1 over 1 plus y over x. You'll have y plus x over x. All of this squared. You see how you're getting all of this? Cancel out the natural logs, they will. You'll have ax. You see this x right over here? We can separate this right here in two separate parts. We'll have y plus x whole square over x square. I've just separated this into their individual exponents. This x square can come across, travel, and you'll have ax cubed is equal to y plus x whole square. If you want, you can leave that as your answer. It shouldn't be wrong. This right here would represent the function or the equation. It may not necessarily be a function, but it does for sure represent the equation for which this differential equation is true. Only a graph would determine if this, or help you determine if this indeed is a function. It would have to pass a vertical line test. Anyhow, the procedure has been laid out for you. This answer is fine. Let's look at this differential equation. Again, it's first order. You cannot cleanly separate the variables right here. You have to do that substitution to enable you to do that separation down the road. You know the substitution is this, y is equal to vx. When you do the derivative of this, you're getting dy over dx, and you know the rest. Product rule helps you determine the rest. You have v plus x dv over dx. Bring in that substitution right there, y equals vx in places of y. You'll have 3 and then vx squared plus 2x vx. This just helps you get to that area down the road where you can separate the variables. 2x vx plus x squared. Remember, wherever I have a y, I'm bringing that vx right here. into those places. That y equals vx is falling into place here. When you open this up, you'll have 3v square x square plus 2x square v over 2x square v plus x square. Isolate the x squares from everywhere. You have 3v square plus 2v, and here you'll have x square into 2v plus 1. You can separate these out, cancel them out. This right here is equal to dy over dx. You know that to be the case because all of this right here was equal to dy over dx, but dy over dx is also equal to that. We can bring it right here, v plus x dv over dx. I want to bring the v onto the other side and do a common denominator. You'll have a 3v square plus 2v divided by 2v plus 1 minus v over 1 is equal to x dv over dx. You have to do a little bit of work here. You have 2v plus 1. Here you have 3v square plus 2v minus v times the common denominator coming here. 2v plus 1 is equal to x dv over dx. When you open that up, and I will open it up, but I'm just removing this part here just for a little bit of space. When I open this up, I'll have 3v square plus 2v minus 2v square minus v over 2v plus 1 is equal to x dv over dx. We have to simplify all of this. You have a 3v square minus 2v square, which is just a v square, plus 2v minus v is just a v. V square plus v over 2v plus 1 is equal to x dv over dx. Now we can separate the variables, and we will. But we will separate everything right over here in this side. And I'm going to erase this side because you've seen it. You know how to do all of this. Let's make that space. From this expression over here, we can separate and bring x on one side, the v factors on the other side, but the v factors will reciprocate. They'll flip around. You'll have 1 over x is equal to 2v plus 1 over v square plus v dv. Bring in the integral sign, and that's exactly what you have. But these cancel out. From this step over here, it's not that hard because you know this is going to bring a natural log x plus c. But if I do that substitution, natural log a new constant is equal to c, I can bring that here in place of this c, and I can bring it into play. This looks seemingly hard, but it isn't. You can do a u substitution here. If u were equal to v square plus v, and then du is equal to the derivative of this, you'll have 2v plus 1 dv. You'll have dv is equal to du over 2v plus 1. And this right here would very easily cancel the numerator out because you would have 1 over 2v plus 1, and then you have a 2v plus 1 all divided by u du. You see how these cancel out, and you can bring in the natural log u, which is exactly what will happen. Natural log u, which is right here, v square plus v. And you can see something which looked like a complex rational fraction was not very difficult to deal with. It easily removed itself by the polynomial substitution technique. You can re-bring in the v values. If y is equal to vx, v is equal to y over x. And you'd want to bring that in here, and let's work over here, and let's combine this. This really here is natural log ax by means of properties of logs, but I want to work in over here. I have a y over x square plus y over x. This is what I have with the v substitution. I have y square over x square plus y over x. Common denominator is x square. I'll have a y square plus yx over x square, all within the natural log. And you're seeing that come into play, and I'm bringing it here, is equal to natural log. We have all of this y square plus yx over x square. But you know, the natural logs cancel each other out by means of the properties of logs. You can cancel them out. It's not anything wrong by cancelling them out. You have ax is equal to all of that. With the natural logs gone, these absolute value signs gone, you can cross multiply the x square. You'll have a ax cube is equal to y square plus yx. You can stop right here if you want. There's nothing wrong with stopping right here. And this right here can very easily represent the equation or the function for which that differential equation was true. The one you see right over here, and the procedure has been laid out for you utilizing this y equals vx substitution and then carrying it through into that differential equation so that the derivatives are removed and everything that remains is a relationship between x and y and this constant coming into play. We did 2 in this particular video. We can look at more practice at another point in time, but that's it for this video. Thank you for watching. Have a good day. Bye.